Okay. All right. So again, just starting out, all these things I'm going to do in the same basic order, right? I got 6 steps that I set up for myself. We just did this like an hour ago, right? So hopefully it's pretty fresh. Basically, we're going to do the same thing. 0 minus condition is a steady state before the switch is moved. Infinity is a steady state condition after the switch is moved, right? The key thing with the steady state, what do we do with the capacitors and inductors? Capacitors and open, inductor is a short. All right, so we're gonna keep going with that. Step three is to get a Thevenin equivalent. So we're gonna do one today that's ugly. Then the differential equation, solve it, get the initial conditions, right? That's our basic steps. Okay. And I'm not going to go through all this stuff because we just talked about it not too long ago. So let's get straight to the example that I've got. It's an ugly looking one, right? I want to figure out IL of t in this particular circuit. IL of t for this circuit for t greater than or equal to 0. Okay. All right, so when I go through those steps, I've written those steps out as basically parts A through F there, right? So part A is my initial condition, IL of 0 minus. So the current before the switches change state. Okay. All right. So what do I do for part A? So step 1, find IL of 0 minus. What do I do? Help me out. Cry a lot. It's an ugly circuit. What's the first thing to do? Short out the inductor, right? What about the switches? Yeah, leave the switch alone. Like, leave it just like it is in that picture right there, right? So that 36 volts and the 2 ohms over there, do they mean anything in this circuit? They don't. All right, they don't mean anything. So basically this guy, I got a 12-volt source. I got 4 ohms over here. The inductor you guys said was a short. I got 6 ohms, and I got this ugly guy here, which is a current-dependent voltage source, right? There's a voltage source that depends on a current, and it depends on the current in that branch. So this guy is 2 times I sub A like that. Okay. Now, what am I trying to solve for? What is it that I want to find? Make sure you guys don't lose me too much on this. What am I trying to find in this particular step? What's that? IA. Well, I'm going to need to know what IA is, but the thing I'm trying to solve for is IL of 0 minus, right? So where is that? Where is that current in this circuit? Yeah, it's the current. Yeah, the inductor is here, right? So basically this guy is here. So whatever the current is in this condition, that's IL of 0 minus. So I just make sure I got this one's gonna be ugly, so I want the answer. So maybe I didn't save it for myself. I did. Okay, good. All right, so how do I start? Any ideas? Or find an IL of 0 minus. Well, all right, I'll give you an idea. Let's use nodal analysis. All right, I could do all kinds of different things. Actually, I got a limited number of choices I could use. For this case, for this thing, I would say I can use mesh or nodal. Why is that? Why mesh or nodal? Got a dependent source. That means I can't do anything fancy with trying to, simplify resistors with series and parallel combinations. I got to do a nodal thing here. Okay. When I do nodal analysis with this thing, right? what do I have to do? One of the nodes has to be ground, right? Which node is that going to be? Yeah, usually it's the bottom one. It could be any node I want, but usually it's the bottom one. Okay. How many nodes are there in this particular circuit? That sounds like a lot. Well, so there's one here, right? And there's one here, right? So it turns out this is actually, turns out I don't really need to do nodal analysis. It's actually simpler than I'm making it out to be, right? Back, yeah, I'm doing nodal analysis, but it's pretty straightforward. What do I really have to do? I just have to figure out what IL of 0 minus is, right? How do I figure out what IL of 0 minus is? I would actually just do a KVL in this particular case, right? And I'd do a KVL around the outer loop. Okay, so what would that look like? So if I do a KVL around the outer loop here, what do I got to do? How would I write that? Negative 12. And then I'm going to say, then I go through the 6 ohm resistor. So again, what I like to do is I like to say, okay, well, it goes plus to minus like that. I'm going to call him V6. All right. So I'm going to go plus V6. Now, what do I do there at the dependent source? How do I write that in my KVL?
Minus 2IA.
Minus 2IA. Why minus? Yeah, because I go from minus to plus on that guy. So minus 2IA. All right, now the way I'd write this is I'd say 12 equals V6. So V6 I want to put now in terms of a resistor and current. Right, so how do I put that in terms of a resistor and a current? Well, IL of 0 minus is the current through that. That's the thing I want to solve for, right? IL of 0 minus times 6. Right? And my algebra teacher would be mad at me. I'm supposed to do that as 6 times IL of 0 minus. Right? What about the negative 2IA? How do I do that? Well, that would be negative 2 times IA. What is IA? 12 over 4. Yeah, because I got 12 volts across that resistor and 4 ohms is the resistor, right? Then I solve for IL of 0 minus from there, all right? So that whole thing becomes, I don't know, IL of 0 minus is equal to 12 plus 2 times 12 fourths. So what's that? 12 fourths is 3. 3 times 2 is 6. Okay, that's 18. All right. Everybody agree with me? That's 18. Mental math's not my strong suit. I think that's 18. What's that? Divide by 6. Did I mess up? Oh, 6IL 0. Thank you. Yeah. Crap. That's the actual equation, right? So 6IL 0 is equal to 18. So IL of 0 minus is equal to 3 amps. All right, that's the final answer. All right, you guys good with me till there? All right. Now I got to get to step 2. What was my step 2? Find the steady state current IL of infinity. All right, so IL of infinity. So how do I approach that? How do I find IL of infinity? What do I got to do? What do I do with the inductor? Sure. What do I do with the switch? Flip the switch to its final condition, right? So now, which of the 2 voltage sources doesn't matter? One of them doesn't matter. Which one doesn't matter? Yeah, the 12 volt source doesn't matter. So get my circuit redrawn. That's the first thing I want to do. I got a 36 volt source. And then I got this 2 ohm resistor. Then I got the 4 ohms again. And the 4 ohms has IA going through it. And then what else do I have? The inductor, we said we make a short. So then I got 6 ohms here. And my very badly drawn 2 times IA source. Okay. One of the things is weird. So we see this later. I mean, dependent sources are real things. They're models for real things, right? So we actually deal with those a lot. Unfortunately, again, the lab and this class don't connect very well, but we see those a lot in amplifiers. So like circuits that, you know, you've dealt with before, like your stereo can be modeled as a dependent voltage source, right? We have all kinds of things. You can't go to the store and buy one, right? But you can build one, and it's a model for what some other circuit's doing. Okay. All right. So there's my thing. What am I trying to do? I'm trying to solve for that IL of infinity, right? Which I've labeled there. How do I do that? Well, this time I am going to use nodal analysis, right? I kind of did before too, but this is definitely nodal analysis. So there's going to be my ground. All right. In this case, how many unknown node voltages do I have? I have one unknown node voltage, I guess, right here. I guess I have sort of I have a node here too, right? And I have this one unknown one, right? So I'm going to call this here. I don't know, what did I call it when I did it? I called it VX. Okay. Right there. Okay. All right. So this is where I know I diverge a little bit from Zybooks. I think the way Zybooks typically does this is when they look at these, they say all the currents go into the node, right? I think, is that the way you guys learned it? All right, I don't do it that way. All right. What I do is completely consistent with what you learned. All right, but here's what I'm going to do is I'm going to write it this way. I'm going to say I got a current going into this node, a current going out of this node, and out of this node, right? Because I've already defined my currents that way. IA goes out of that node, IL infinity goes out of that node, and whatever current I have over here goes into this node. All right, I'll call this, I don't know, I2. Okay. So the way I start my KCL, or well, the way I start my nodal analysis is I just write KCL. That's what nodal analysis is it's KCL, right? I go to a node and I write KCL. The way I write KCL is instead of everything going into the node, when you do it as everything into the node, you say everything into the node equals 0, right? That's the way you probably were writing it. The way I do it is I say everything going in equals everything going out, right? It's the exact same statement, all right? So if I'm saying everything going in equals everything going out, I'm saying the going in is I2. The going out is IA plus IL of infinity. Like that. You guys with me there? The current going into the node is on the left side. The currents coming out of the node are on the right side. Entirely consistent with the arrows that I drew right there. Okay. All right. What is I2? Help me define I2 in terms of the node voltages. Actually, even simpler than that. In terms of, so I said I2 is the voltage of, I2 is the current through that 2 ohm resistor, right? So the way I would write that is I would say it's V2 divided by 2 ohms, right? I don't like to jump right to, I know you guys like to jump right to the nodal equation, right? I don't. I like to say the currents, I write my KCL first, then I get my KCL in terms of the resistors, and then I get that equation in terms of the node voltages, right? Take it slow and you'll be able to follow it more methodically. Okay. What about I sub A right there? V4. Yeah, V4 divided by 4 ohms. What about IL of infinity? Well, that would be V6 divided by 6 ohms. Right? So V6 was the voltage across that 6 ohm resistor. V4 was the voltage across that 4 ohm resistor. Now what I'm going to do is I'm going to say I can write all those things in terms of the node voltages, right? So let's do that. V2, V4, and V6. All right. How do I define V2 in terms of the node voltages? Well, I do that by looking at the positive terminal and the negative terminal and saying it's the voltage of the positive terminal minus the voltage of the negative terminal. Okay. So what's the voltage at the positive terminal on that 2 ohm resistor? 36. This guy's going to be 36 minus whatever I have at the negative terminal. What's that? Vx, the unknown. Okay. Now what about V4? That guy at his positive terminal has Vx. What node voltage does he have at his negative terminal? 0. So he's just Vx. Okay. What about for V6 right there? What's at his positive terminal? Yeah. Vx. What's at his negative terminal? 2IA. Yeah, and this is the important thing. It's actually not 2IA. It's minus 2IA. So Vx minus 2IA, sorry. That's why I'm saying it's helpful to keep it slow because I got all kinds of minuses and pluses and all kinds of stuff. So I got a minus and a minus makes a plus. This guy is actually Vx plus 2IA, right? And what's IA? IA is what? Vx over 4. Yeah, exactly. So this guy becomes Vx plus 2 times Vx over 4. All right. Then what I do is I put all that together into one equation. All right. So I have this. So what did I have? I had V2 over 2 equals V4 over 4 plus V6 over 6. That was the equation I had on the last slide. And I said that V2 was equal to 36 minus Vx. V4 was equal to Vx. And V6 was equal to what? Vx plus 2Vx over 4 or 1/2 Vx. 3/2 Vx. Right, like that. So what do? I put all that into this equation now. I say this V2, this 36 minus Vx over 2 equals Vx over 4 plus 1/6 of 3/2 Vx. Like that. Right? That whole thing. And if you do that math, you'll get an answer. I didn't write down what it is. I didn't write down what it is. Right, but if you solve that, you'll get down what it is. Yeah.
Wait, so isn't 2IA the current source? Voltage?
Well, so that's a current dependent voltage source.
Okay.
Right? How do I know that? So the key thing when I look at this guy, I see that he's a voltage source, but he depends on a current. Right. And again, those things happen in the real world. That actually happens pretty often in a transistor circuit, right? That what we get is a voltage source whose voltage depends on the current somewhere else in the circuit. All right, so we would solve that to figure out what Vx is. All right, and once we had Vx, right? Once we have Vx, I guess what I would do is I would say, well, then I have to figure out what IL of infinity actually is. Well, how would I figure out what IL of infinity actually is once I know what Vx is? I do what?
Do you find the voltage across IL?
Well, remember the circuit, yeah, so the circuit we're looking at is that circuit now, because we're looking at the steady state condition, so the inductor itself is gone. Right, so I'm looking for the voltage across that 6 ohm resistor, right? So I would say it's the voltage across the 6 ohm resistor, which would be V6 divided by 6. Or the 3/2 Vx divided by 1/6, right? This current right here, this current is IL of infinity. All right. I guarantee there's gonna be a problem like on the first exam where there's gonna be dependent sources and current sources. One thing I want to check when I write my KCL equation, all three of those, and this is why I like looking at it like this, all three of these things have what units? I had a voltage divided by a resistor. Right? All of them are amps, right? All of them have units of amps, all of them are currents. I guarantee on the exam, I'm gonna go, half of you guys are gonna write these things and you're gonna have a voltage plus a voltage equals a current, right? And I know the problems I'm gonna give you to screw those up, all right? But this, make sure you check that. It better be sure that everything in my equation is amps like this, right? All right, so make sure you do a check on them. Where this gets you screwed up is I'll see people with a voltage source hanging there on one side or something like that. And they'll have a voltage source equals an amps plus an amp. Right. All right. And we can do some examples like that maybe later. All right, you guys follow what I did here? All right. All right, so that was step 2. Now we got step 3, which is the ugly part. I got to get this guy down into an equivalent circuit. Now I'm dealing with the transient period here. So if I'm dealing with the transient period, what do I do with the switch? It's in the second position. And before I even get too far, right, I want to get to an equivalent circuit, meaning from the perspective of the inductor, I want everything else to look like a Thevenin equivalent, right? So again, what's a Thevenin equivalent look like? What's in it? Yeah, voltage source in series with a resistor. So I better have VOC R Thevenin and I sub L like that. Okay. So the thing, and you may see me, I think sometimes in the homework I call it VOC, sometimes I'll call it V Thevenin. Either way, it's the open circuit voltage. All right. So if that's not clear, it's always the open circuit voltage. So what, all right, open circuit voltage of what? What do I do here? I want to find the equivalent circuit that's seen by the inductor. So where do I start? Well, I remove the inductor. And I do it when the switch is at position 2. So the circuit I'm dealing with, there's my 36 volts, my 2 ohms, my 4 ohms. Then I basically say I'm removing the inductor. Six ohms, and then this goofy guy. This 2 IA, where IA is like this. Okay. So I want to find the Thevenin equivalent looking into these terminals right here.
Don't we still have to put the 12-volt branch there, which is, you know, like,
I could put it there, but what do I know about it? If the time period that I'm worried about is when I'm at position 2 on that switch. Okay. When I'm at position 2 on that switch, is that 12-volt source doing anything? Is he going to create any current flow in the circuit? No. So basically, I don't need him. Okay. He's not going to cause any current flow in that circuit, so he's gone. All right. So I'm basically in this setup here. All right. So what do I got to do? Well, I'm trying to find a Thevenin equivalent, which means I got to find 2 things, right? I got to find the open circuit voltage, and I got to find that equivalent resistance. So how do I start? first of all, in this case, I got a dependent source set up, right? When I have a dependent source set up, it makes the whole Thevenin equivalent thing harder, right? What do I have to do if I have a Thevenin equivalent with a dependent source? How do I get that RTH? Yeah, okay. So basically what I got to do to get this RTH, there's two ways to do it. You can do this test source approach. I think I heard somebody saying that. Perfectly fine if you want to do it that way. The way I'm going to do it is the other way you learned it. Where I know learned is in parentheses, right? You're still learning it. I get it, right? That's why we're doing this, right? VOC divided by I short circuit. All right. So basically, we got to figure out what VOC and I short circuit are. So VOC, what's VOC? What's the meaning of it? It's the open circuit voltage. So it's the voltage when there is nothing at the terminals, right? What is I short circuit? What is that? Physically, what does that mean?
The current and the voltage short is shorted.
It's the current when there is a short across those terminals, right? It would be, so VOC is the voltage here at these terminals. So right now in this setup, this would be VOC. I guess I'll write it like this. It's a DC. For DC stuff, I write capitals like that. So VOC, I short circuit would be the current flowing in this setup. If I put it short right here, I short circuit would be that current. All right. So for now, I'm going to start with VOC. Now, let me be clear. This is going to be more work than I would probably give for a test problem. All right. This is a lot of work that we're about to do. One problem would not have this much work. However, this is a good practice for all of the stuff that would be on the test, right? So this is a good problem to go through. But again, more difficult. This is a couple of steps beyond what I would expect on a test. All right. But every bit and piece of this could be its own problem, probably. Okay. All right. So how do I find VOC? Well, you got the right idea. It's not going to be VX from the previous problem because the circuit's different. Okay. But I could think of it that way. I could do nodal analysis here and say, okay, well, I want to solve for this VX. And then I want to solve for what the voltage is at this point right here. Right? You can't see what, okay, your voltage at that point. And I could say VOC is VX minus whatever the voltage at this point is. All right. So, all right, so let me redraw that over here because let's do it over here. How much space did I leave myself? All right, so 36 volts. What was that resistor? Is it 2 ohms? 2 ohms. This is IA. IA. 4 ohms. This is VOC. Here's my 6 ohms. And this is 2IA over here. Okay. All right. So how much current flows in this loop over here? None. Right? There's no current flowing over there. Why? There's an open circuit over there, so I can't have any current flowing, right? So all the current from that 36 volts is flowing where? Basically in the 2 to 4 ohm resistor, all that current's flowing there. So I got a voltage divider again, right? So I can say, so if we still want to call this VX, we can do that. Right? VX right there, the voltage at that node is the same as the voltage across that 4 ohm resistor. Right? So VX is equal to what? Using the voltage divider. So we said voltage divider is basically the current in the loop times the resistance that current's flowing through, right? So what is that? 36 volts divided by what gives me the current? Divided by 6 gives me the current. Multiply that by what to get the voltage? 4. Right, so what is that equal to? That's 24, right? Okay. Now, VOC is Vx minus whatever voltage I have at the negative terminal. What's the voltage I have at the negative terminal, right? What's what? Yeah, 0 is the logical guess, right? Because how much current's flowing over there? None. However, that's not right. Well, I got a voltage source over there, right? So how much, so you are correct in saying how much voltage is there across the 6 ohm source, or that 6 ohm resistor? 0 volts across the 6 ohm resistor, right? Because there's no current. I times R is 0 if I is 0, right? So there's no voltage there, but there is a voltage in that 2IA, right? Because that is a voltage source, right? So if I look at this, it's telling me that if I did a KVL around that loop, right? What I would see is, and we can do that real slow if you want. If I do a KVL around this loop here, right? What do I see? I see that 0 equals minus Vx plus VOC, right? Plus whatever V6 is, minus 2IA, right? I did a KVL around that loop, right? Where I called this V6, like that. Now, V6, the voltage on that 6 ohm resistor is, we just said, 0, right? So that tells me that VOC is equal to Vx minus 2IA. Like that. Yeah.
Why is Vx negative?
Well, Vx is negative of the way I wrote my KVL there because Vx is the voltage across this resistor. So it's basically going minus to plus like that. Right, because it's just based on the signs that I have for my voltages that I picked. Okay. All right, so Vx we already found is 24, so we're good with that. So in this case, I say this is 24 plus 2 times IA. What's IA? I already know what that is, don't I? What is that? The current in the 4 ohms, right? So what would that be? 6 amps, right? It was 36 divided by 2 plus 4, right? So 36 divided by 6. Oh boy. So let's see. 36 divided by 6 is 6. 6 times 2 is 12. Yeah, 24 plus 12 is 36 volts. Okay. All right, so we got that done. All right, questions about how we got to that? This is a tricky one because I know a lot of people said, so whatever, this is Zach. What's your name? Wes. All right. One of your friends is Zach or something. All right. All right. Well, at least I got it's close. I know mine was close. All right. So what he said, what Wes said basically was that, you know, the voltage across the 6 ohm and the 2IA was going to be 0. A lot of people would say that. A lot of people would in fact probably say VOC is 0, right? There can be a voltage across an open circuit. There's no current through it. The current through an open circuit is 0. The voltage across an open circuit is just defined by whatever the heck the rest of the circuit's telling it to be. All right, and that's the thing that we got to remember. KVL tells us what it's going to be. All right, so we used KVL to figure it out. All right, now that helps me with my VOC. The other thing I needed to do is to figure out the R Thevenin, right? In this case, because it's got a dependent source, we already talked about this. The dependent source means that what I'm going to do is I'm going to try to find the I short circuit and use VOC and I short circuit to figure out what the Thevenin resistance is going to be. All right, so what do I do in that case? I got to find I short circuit. So for I short circuit, what do I do to these terminals here? Short them. All right, and I short circuit, it's always defined to go from the plus to the minus terminal. So there's I short circuit like that. All right. What's my best bet for this guy? Well, my first thing is going to be to draw this on another slide because I'm going to run out of space pretty quick. Okay. So 36 volts, 2 ohms. Four ohms, where this current is supposedly IA. I short circuit is here. My 6 ohms is here. And then I have this voltage source here, which is 2 times IA like that. All right. I got a couple of ways I can do this, right? I can do mesh or nodal. We're gonna do mesh. All right. And I know you saw this on the homework, right? On the homework, I tell you to solve the problems a particular way. You'll see on the practice exam, I will tell you to solve the problems a particular way. Several of you will be unhappy when you take the exam and you find out that if you don't do it the way I told you to do it and you get the wrong answer, you're not going to get credit. All right. So ABET accreditation says you're supposed to learn all these different methods. I'm going to test you on all those different methods. All right. I'll give you some credit for getting the right answer, but I won't give you the full credit if you don't do the right method. All right. So pay attention to what the instructions say. All right. I want you to know all the different approaches because they're all useful for something. So the reason I say that is because some people are like, wow, I like mesh. Some people say I like nodal. All right. Well, you need to know both. Okay. So in this case, I'm going to do mesh. All right. So I'm going to call this over here. I don't know. What did I call it in my, I'll call it I1. All right. And the mesh current on this side, I'm going to call ISC, right? Because it's going in the same direction. So I got I short circuit is my mesh current over here. And I1 is my mesh current over there. All right. Okay. So for me, when I do a mesh, basically what I'm going to do is when I write out mesh stuff, what I do is I'm writing what kind of equations? KVLs. All right. So I just do everything going clockwise. So I'm going to look at the left mesh here. So the left mesh 0 equals. All right. So I start in the bottom corner there and I go around clockwise. So how do I write that for the left mesh? Negative 36. Again, I'm going to go slow. I'm going to call this V2. I'll call this V4. Call that V6. I'm going to say I have plus V2 plus V4. Like that. Okay. So I'm going to rewrite this and say I got 36 equals, what is V2? Well, I want to put in for V2, I want to put in the mesh current now. 2I1. And what's V4? Well, that would be 4 times I1 minus I short circuit. Like that. Okay. And why minus? Because I1 goes into the plus terminal and I short circuit comes out of the plus terminal. Right? That's why I wrote it there. All right, that deals with the left mesh. Now about the right mesh. So again, I'm going to start in this corner and I'm going to go around counterclockwise. 0 equals. So since I go minus the plus on the 4 ohm, I'm going to write just minus V4. Now I know you guys like to go to writing that immediately right away in terms of the currents, right? I don't. Right? The reason I don't is because there's so many minus signs to keep track of. My brain's too small to think about it that way. If you think yours is bigger than mine, good for you. All right. Take it slow. All right. Take it slow and you'll save time in the end, trust me. And you'll be more likely to be right. Like I said, on the exam for like these mesh and nodal problems, I'm not so worried about the numbers, whether you got 2 amps in one and 1 amp in the other. I'm more worried about you understand the approach, how to write the equation. All right. If you understand the approach, how to write the equation, you'll get the math right if I gave you more time. Okay. All right, so focus on getting it right. All right. So keep up where I'm going. 0 equals negative V4. Then what do I do with the 6 ohm resistor? Plus V6. And then what? Minus 2IA. This is why, because that the polarity of that source going from minus to plus is going to mess with your heads. All right. So 0 equals minus V4. So, all right, minus V4. So now I want to put that in terms of Ohm's law. So minus 4 times what?
Negative I1.
This is why I'm doing it this way, right? So V4 as I've written it there is 4 times I1 minus ISC. To just be clear about that, right? And then V6 would be equal to 6 times I short circuit. Like that. So when I write this out, I say minus 4 times I1 minus I short circuit. Right? Again, rather I like to write it down so it makes it easier for me in my small brain to track the minus signs, because there's lots of them here. All right. So you guys follow what I did there? KVL gave me a minus sign on the V4. All right. Ohm's law told me, using the passive sign convention, that V4 is equal to 4 ohms times whatever the current going into the plus terminal is, minus whatever current's coming out of the plus terminal. Right. So this relationship is Ohm's law with the passive sign convention. This one is KVL. I got all kinds of reasons for minus signs to appear, so take it slow. Okay. Questions still?
So it would the V4 equation would always it would always be I1 minus ISC. It doesn't matter which you're doing.
It's I1 minus ISC because of the way that the polarity of V4 has been defined. Right?
So if you're a ISC minus I1, would that be incorrect in this case?
If I said so in my KVL, it's going to end up being ultimately 4 ISC minus 4 I1. Right? In my KVL, it's going to end up being that way. But the key thing is there were 2 minus signs. I got a minus. So based on the way I defined V4, I have to make sure that this equation is set up consistent with the passive sign convention. And I have to make sure that this equation is set up consistent with the signs in KVL. Right. There's a lot of negative signs to track. Right. So that's why I said try to keep it step by step. It makes it a lot easier to do it. Okay. All right. So, all right, let me keep going though. All right, what do I do with V6 there? Yeah, that one's just plus 6 ISC. And then I have minus 2 IA. All right, so that's minus 2 times IA. What is IA? IA is the current in that middle branch, which just, again, looking at the arrows, right? IA is basically whatever I1 is minus whatever ISC is going against it. So it's minus 2 times IA, sorry, I1, which is going with IA, minus ISC, which is going against it. And because of that minus part of the 2, there's going to be all kinds of ugliness here. So if I rewrite this character, I get 0 equals, oh boy, should be minus 6 I1. And then that, what happens with the ISCs? I get 4 ISC plus 6 ISC plus 2 ISC. So it looks like it becomes plus 12 ISC, I think. And then this guy becomes over on this side 6 I1 minus 4 ISC. Now, this isn't a math class. It's not a MATLAB class. You solve that however you want to solve it, right? I got two equations and two unknowns. So the way that I would do that is I put that in matrix form. All right. Now I put a video on Canvas. I don't want to close this out. I'll show the video at the end, but I have an extra video section on the main Canvas page. One of them shows you how to solve a system of linear equations in MATLAB. MATLAB stands for Matrix Laboratory. It's meant to deal with everything in matrices. So it's really, really good at this. Okay. What would I do? I would put this into matrix form. And there it is right there, right? So 0 equals -6i1 plus 12isc. That's one of the equations. And the other one is 36 equals 6i1 minus 4isc. Okay. So what I do is I set this guy up in matrix form, and I basically do it like this. So hopefully most of you guys have seen matrices in your algebra. All right. You'll definitely see that with Yahoo in 2254. If you're not comfortable with what I'm doing, then don't. You can do it other ways, right? So I would write it like this. And you could do substitution. Substitution would get awfully ugly if I get to 3 meshes, right? All right, so it looks like that. Now, the way that I set this up is I say, all right, this looks to me like B equals A times X, right? And what I want to do is I want to solve for X. And what I did here is I wrote this out. So in MATLAB, and again, I have an example where I do this slow in MATLAB, but you guys need to know this anyway. Here's the A matrix. All right, and let's take a close look at what I did. I wrote the top row of this matrix is -6, 12. The bottom row is 6, -4. If you don't like this, again, don't worry about it. All right, turn your brain off. You do want to know it, then just follow along. -6, 12, and then I put a semicolon in there. And even before that, I put brackets. Brackets are how I define a vector or a matrix in MATLAB. Okay. Generally speaking, you guys aren't going to need to know that for this class. You will need to know that for 2254. But if you want to use this approach, I see brackets. Okay. And -6, 12. And then I put a semicolon. What's a semicolon do? Makes a row, right? So what I see is I got -6 and 12 in the top row, and I got 6 and -4 in the bottom row, which is exactly the way this guy looks. All right. And then for this B vector, which is just, a column of numbers, I did 0, semicolon 36, which puts a 0 in the top row and a 36 in the bottom row. Now to solve for X, I basically say that it's A inverse times B. That's what you learned in linear algebra if you took that. All right. The way you do that in MATLAB is you say inverse of A times B, like that. All right, and it'll tell me the 2 answers. So just to be clear then, I got 2 answers here. 9 and 4.5. Which one is which current? Which one is I1 and which one is ISC? Yeah.
One is a 9 SC.
Yeah, I1 is the top one and ISC is the bottom one, right? So if I wanted to access this, let's say I called this X, right? I didn't in my example. Let's say I called it X. X equals inverse A times B. This would be, if I wanted to access the number X of 1, and this guy would be X of 2. All right, but the important thing is this is I1, and this is ISC, right there. All right, we just did a lot of work. What the heck were we doing it for? Trying to find R Thevenin, right? To find R Thevenin, we had to find I short circuit, which we just did. All right, I short circuit is 4.5 amps. So my R Thevenin, is VOC divided by I short circuit. So VOC was, I don't even remember anymore. 36 volts, okay. And my I short circuit was 4.5 amps. That's probably a nice number. I think it's. Oh boy. What is it? I thought I had it written down. I think it's 18. Eight. Yeah, 8. All right, 8. All right, 8 ohms. All right, so what we were trying to do is we were trying to say we were trying to figure out what the inductor current. So back to our original circuit, we've been doing this for so long, it's hard to remember what we were doing. We were reducing this thing down to an equivalent circuit like this, right? So that's the equivalent circuit we're trying to get it to, right? So now I know what R Thevenin and VOC are. So this guy is my VOC. This guy's my R Thevenin. Here's my L. There's VL. There's IL. All right. So to do this, I'm going to write my KVL, right? So do my step 4 of my process, which is to write my differential equation. So how do I do that? 0 equals what? Negative VOC. Then it's going to be plus IL times RTH. And then plus V sub L. So 0 equals, sorry, I'm going to move VOC over. VOC equals IL times RTH plus V sub L. Now, I want a differential equation in terms of, I'm solving for what again?
A.
What's that?
A.
A.
Yeah, well, with after the equation.
Well, I mean, yeah, what's the quantity I'm trying to figure out? What variable am I solving for? What's that? Yeah. The inductor current, IL, right? So this guy's not quite, he's in terms of IL and VL right now. So I gotta get rid of VL. How do I get rid of VL? I can't divide by R Thevenin. I need, what's the relationship between the inductor current? Yeah, you got it. So this, nobody remembers those ones, right? It's hard to remember those. VL equals L DIL by dt. That's basically Ohm's law for an inductor, right? VL equals L DIL dt. So I got VOC equals IL times R Thevenin plus L DIL by dt. Now that's not the standard form, it's close to it, right? My standard form that I gave you that I like to follow and the book follows is I want a constant equal to x plus tau dx by dt. So I want to get, basically what I want that to look like is a constant equal to IL plus tau times DIL by dt. So what do I have to do to get IL by itself in this whole thing? Get back to where it was. Went too far. Where is it? There it is. How do I get IL by itself? I now have IL times RTH. How do I get that by itself? Yeah, divide both sides by R Thevenin, right? I'm going to have VOC divided by R Thevenin equals IL plus L over R DIL by dt, right? What's my tau here? Yeah, so, and I guess R Thevenin. So my tau is L over R Thevenin. Okay. So if I put in the numbers VOC, so VOC over R Thevenin equals IL plus tau DIL by dt. VOC was equal to, what was it? I don't even remember it anymore. 36 volts. R Thevenin was 8 ohms. Okay. So tau was L over R Thevenin. What was my L? I don't remember. 3 Henrys. So this is 3/8. Okay. So that tells me if I go back and look at the form of the answer, IL of t is equal to IL of infinity, whatever the final value is, plus A times e to the negative t over tau. Right? I know what IL of infinity is. I solved for it a long time ago. IL of infinity is a number. I think if I go through that math, that should work out to be 4.5 amps. Okay. That's 4.5 E or 4.5 plus A E to the negative T over tau. I know everything there except one thing, don't I? What do I not know? A. So I put in IL of 0, which we solved for a long time ago. IL of 0 was 3 amps. Right? So I have that's 3 amps equals 4.5 plus A times E to the 0, which is 1. All right, so I can solve now for A. All right, what's A going to be? It's going to be minus 1.5. And we're done. Okay. Finally. Again, more involved than you'd see on a test, but we got a lot of stuff going on in a problem like this, which is a good review. Okay. All right. 3:37. I've got 5 plus 2, 7 minutes left. 5, 8 minutes left. I can start an example if you guys want some, but I was just going to end probably. If you guys got questions, feel free to come up and ask me. Yeah, come on up and. Yeah.